Welcome to the second episode of Explore Space with me. A lot of us know how gravity works on Earth. A heavier body pulls a lighter body towards itself due to its mass and blah blah blah. But how many of us actually know how gravity works in space? So, what is gravity? Gravity is the force by which a planet or another body draws objects towards its center. The force of gravity keeps all of the planets in orbit around the Sun. Anything that has mass also has gravity. Objects with more mass have more gravity. Gravity also gets weaker with distance, so the closer objects are to each other, the stronger their gravitational pull is. Earth's gravity comes from all its mass. All its mass makes a combined gravitational pull on all the mass in your body. That's what gives you weight, and if you were on a planet with less mass than Earth, you would weigh less than you do here. We as humans living on Earth also pull Earth towards us with the same force of gravity exerted by Earth on us. However, due to its massive size of the Earth, the force of gravity exerted by us on Earth has no effect on Earth. However, this is the Newtonian law of universal gravitation. In order to understand how gravity works in our universe, we have to understand certain concepts first. Often in astronomy and astrophysics, we hear the word space-time continuum, or space-time, but rarely do we as laymen understand the true concept of space-time. Space-time refers to the physical and mathematical model of the three dimensions combined with another dimension which is time into a single four-dimensional continuum. In space-time, the universe is represented as a fabric where space and time are inextricably intertwined. Space-time allows us to describe occurrences of events in terms of both location and time. Imagine space to be a stretched fabric with galaxies, stars, planets, and various other elements of our universe placed on it. When these bodies exert a certain force due to their mass, the space-time bends and curves under the weight. The heavier a body, the greater will be the curvature of the space-time fabric around it. This is called general relativity and explains how gravity works in our universe, which was first formulated by Albert Einstein. In celestial mechanics, an orbit is the curved trajectory of an object under the influence of an attracting force. Alternatively, it is known as the orbital revolution because it is a rotation around an axis external to the moving body. Examples for orbits include the trajectory of a planet around a star, a natural satellite around a planet, or an artificial satellite around an object or position in space such as planet, moon, asteroid, or Lagrange point. Normally, orbit refers to a regularly repeating trajectory, although it may also refer to a non-repeating trajectory. To a close approximation, planets and satellites follow elliptic orbits, with the center of mass being orbited at a focal point of the ellipse, as described by Kepler's laws of planetary motion. Planets revolve around a star, a natural satellite around a planet, or an artificial satellite around an object or position in space such as a planet, moon, asteroid, or Lagrange point. For most situations, orbital motion is adequately approximated by Newtonian mechanics, which explains gravity as a force obeying an inverse square law. F is equal to g m1 m2 divided by r squared. However, Albert Einstein's general theory of relativity, which accounts for gravity as due to curvature of spacetime, with orbits following geodesics, provides a more accurate calculation and understanding of the exact mechanics of orbital motion. Geodesic is the shortest distance between 2 points in a curved space, which is traversed by a celestial body and is the generalization of starlight line to curved spaces. Light in space travels at the speed of 299,792,458 meters per second. Light in space does not travel in a straight line. Light, too, in space follows the shortest path in a curved spacetime. The curved path followed by light is called geodesic, as discussed before. The light is not bent, rather, the path of the light is itself warped due to stars, galaxies, or any other celestial body, which is why, from the perspective of the observer, light in space appears to be curved. There are huge telescopes which are launched in space, which allow us to watch distant stars, nebulas, and galaxies in deep space and observe a spectrum of reflected light which our eyes can't even perceive. They measure near-infrared light, rather than optical light our eyes see. These telescopes operate in an analogous way to digital cameras. First, the telescope collects lots of light from a source. Cameras use lenses. These telescopes are so large that they use mirrors. Then it is focused on a detector, which is much more sophisticated analog of a sensor on a digital camera. The Hubble Space Telescope is a space telescope that was launched into low Earth orbit in 1990 and remained in operation for 35 years, and is still in operation. It was not the first space telescope, but it is one of the largest and most versatile space telescope that is renowned as a vital research tool. It was the first telescope to confirm that supermassive black holes exist. It was the first to prove that black holes are at the core of almost all galaxies. It produced the first images of the collision of two astronomical objects. It was the first to detect oxygen in a satellite's atmosphere. It had the first images of a star's surface other than our sun. It discovered the first exoplanet atmosphere which was detected and elements determined. The James Webb Space Telescope is a space telescope which was launched recently to conduct infrared astronomy. It is the largest telescope in space and is equipped with high resolution and high sensitivity instruments, allowing it to view objects too old, distant, or faint for the Hubble Space Telescope. The picture that is showed on the screen is a comparison of the picture of the same nebula that was taken by the Hubble Space Telescope and the James Webb Space Telescope, and it is clearly visible that the James Webb Space Telescope produces much higher resolution pictures which are much more of the higher quality than that of Hubble Space Telescope. The Webb was launched on 25 December 2021 on an Ariane 5 rocket from Kourou, French Guiana. In January 2022, it arrived at its destination, a solar orbit near the Sun-Earth L2 Lagrange point, about 1.5 million kilometers from Earth. The telescope's first image was released to the public on 11 July 2022. Through JWST, our first look at moons in the making is quite different from how planets are formed from stars. The picture that you're seeing right now on the screen is a fictional picture which is showing the atmospheric composition of a moon in making. PSR J2322 2650b is a Jupiter-sized planet which orbits a pulsar, a dead star spinning so fast it completes one rotation in milliseconds. The pulsar's gravity is so intense that it's squeezing the planet into a lemon shape. But here's the only true bizarre part. Its atmosphere is made of pure molecular carbon. Not carbon dioxide, not methane, just straight up C3 and C2 molecules floating around with helium. Soot clouds drift through the air, and deep inside those carbon clouds condense and rain down as diamonds. Out of 150 planets studied by the JWST, none than this planet showed any trace of molecular carbon in its atmosphere. JWST was used to study galaxies from just 2 billion years after the Big Bang and found that they're making stars way faster than predicted. These infant galaxies had bursty star formation. They would suddenly produce stars at rates much faster than anticipated that early in the universe's history, when things were still getting organized, but somehow nature was doing it anyway. It's like discovering that baby galaxies went through growth spurts which changes our entire timeline of cosmic evolution. Thank you for watching this video to the end. We come to the end of our lesson. Please like, share, and subscribe to my channel. And please also check out my website.